Hi, this is a quick discussion of circular motion, and in particular, we're going to talk about radians and arc length, and how arc length is related to linear distance around a circle. So circular motion is motion around any circular arc. You don't have to go all the way around a circle. You could just make really any turn with your motion. That's circular motion because we can describe it as part of a circle. Whenever we're in circular motion, as we can see here, our velocity vector is always going to point tangent to the circle because it's always pointing in the direction we're moving, and we're moving along that circle. Now, even if we're going at a constant speed, that velocity vector is actually always changing because it's changing direction. And since that vector is changing direction, we are accelerating. Our velocity is changing, and we are always going to be accelerating. If we're going at a constant speed, that acceleration actually is going to point towards the center of the circle, inward radially, we will say. But we could also be speeding up or slowing down as we go along that circle, in which case some of our acceleration is pointing towards the center of the circle to change our direction, prevent us from going off in a straight line, and some of our acceleration can point along the circle, either forwards or backwards, to speed us up or slow us down. And so when we're dealing with circular motion, it's often useful to break things down into a radial component of motion, which points either inward or outward along the radius, and a tangential component of motion, which always points tangent to the circle, either forward or backwards. And even though our velocity is always going to be tangent to the circle, our acceleration can have both a center pointing component, a radial component, and a tangential component. And if we add those two vectors together, it'll give us our total velocity. They're perpendicular, so we can just use standard vector addition. And in fact, if we have two perpendicular vectors, radial and tangential, that describes any motion, although it's more useful for circular than anything else. Today we're just mostly going to focus about tangential motion. We're not really talking about acceleration. And we wanted to find first, we want to define our unit of angle whenever we're going in circular motion. We don't usually use degrees. We usually use this unit called radians. And radians are a dimensionless unit. They're defined as arc length, which is distance around the circle. Maybe I'll call that S, divided by the radius R. So because they're defined as a length over a length, it's going to be meters over meters, they actually don't have any units. Or they're a dimensionless quantity, the same as if we're counting the number of people. It's the number of radians we are going around a circle. But so we don't get it confused, this dimensionless quantity, with other dimensionless quantities. We do usually stick the unit radian on at the end, just so we know what we're talking about. And really all you need to know about radians is that one full cycle around a circle then is 2 pi radians. And also that's 360 degrees. Which also means that half of a cycle is pi radians, or 180 degrees. The data booklet does give you this handy conversion if you ever forget how to convert between radians and degrees. A radian is 180 degrees over pi. If we wanted to convert to degrees, we would just solve for the degrees. We have a nice little conversion factor there. So what are these quantities in radians? Well, 66 degrees is how many radians? 180 degrees is equal to pi, so we could multiply by pi over 180 degrees to convert to radians. That is pi radians over 180 degrees, getting a little messy there. So it just becomes 66 times pi over 180 is 1.15 radians. How about a left turn at a T intersection? Well, that's a 90-degree turn. So 90 degrees is how many radians? Well, it's a quarter of a cycle. And if a full cycle is 2 pi, then 90 degrees is going to be just 2 pi over 4, which is pi over 2 radians. And since this is physics, we're going to write it in decimal. Pi over 2 is about 1.57 radians. How about riding a Ferris wheel through 11 full cycles? So maybe we ended up where we started, but we still went an angular distance, a certain number of radians. We went more than 360 degrees. So let's find the total angular displacement we went through. 11 cycles, and there's 2 pi radians in each cycle, so just 11 times 2 pi to get our answer. 11 times 2 pi gives us 69.1 radians. So yeah, we always have to use radians for circular motion because radians let us easily convert between our angular motion, theta, and our arc length. And the equation that relates arc length to angle only works in radians, or at least it only works well in radians. It makes it much easier in radians. Arc length is equal to the radius times angle, as long as our angle is in radians. So let's identify the arc lengths for, well, for these two. A left turn at a T intersection with a turning radius of 60 meters. Well, we know that that was pi by 2 radians. If we want to find the total distance traveled, delta S is equal to R times delta theta. So it's just going to be 6 meters times pi over 2 radians. That's about 9.42 meters. Okay, how about our Ferris wheel? What is the total distance we've traveled around that Ferris wheel if it's 120 meters in diameter? Well, we know our angle that we traveled through was 69.1 radians. So our arc length is just going to be, it's the radius. This is the diameter. So the radius is just 120 over 2. That's 60 meters times 69.1 radians, which is equal to 60 times 69.1, 4,150 to 365 meters. Notice that the radians just kind of disappear when I convert to an arc length or distance. That's because, again, radians are a dimensionless quantity. So we have to keep track of when we're in radians and when we're not in radians. We can't always do our unit cancellation to get our proper unit in the end because radians are dimensionless. But anyway, that's basically it. Just keep in mind that this equation is not in the data booklet. And delta S is the variable we usually use for displacement, but it's also sometimes used for arc length. Keep in mind that in this context, it is not a displacement. It is an arc length. It's really a distance around the circle that we've gone. And that's all for radians. Bye.